Hello and welcome to today's webinar in partnership with Husky, hosted by Packaging Europe. Today we'll learn about bioresins and how to successfully leverage the material that can be the foundation of a transformative shift in the injection molding landscape. My name is Elisabeth Skoda. I'm one of the editors at Packaging Europe. For those of you who aren't familiar with Packaging Europe, we are the leading intelligence resource for European packaging professionals. Via our magazine and website, as well as online and in-person events such as the Sustainability Awards and Sustainable Packaging Summit, we deliver daily news content, authoritative comment and analysis, case studies, and high-profile interviews with leading industry players, and we enable communication across the packaging value chain. So for today's webinar, we are joined by Oliver Schindler, who is the team leader of the Hot Runner Application Engineering Team EMEA at Husky Technologies. A bit more about today's webinar. Bioresins, also often referred to as bioplastics, biopolymers, or biomaterials, can enable molders and packaging producers to navigate consumer trends, legislation, and sustainability goals. However, their properties can throw up a range of challenges due to their physical properties, temperature sensitivity, and evolving performance characteristics. In today's webinar, we'll find out how these innovative materials can be successfully leveraged. We'll hear about bioresins' growing popularity, the diverse spectrum used in injection molding, challenges around the materials, best practice and application example. And we'll learn about Husky's technology capabilities to enable success with bioresins. Before I hand over to Oliver, just a little bit of housekeeping. There are 15 minutes at the end of this webinar reserved for a Q&A. Using the chat facility, please direct message us with your questions and we can put them to a presenter at the end of the session. You can do this throughout the entire webinar and we'll try to get as many of your questions answered as possible. For any technical questions, please select the support button, which you will see on the left-hand side of your screen. And for any streaming-related issues, you can also use the help button on the bottom right of the stream window. So with that, I'd like to hand over to Oliver for the presentation. Thank you.
Thank you very much, Elizabeth, and good afternoon to everyone here in the audience. Just give me a second. I'm starting the presentation now. So I'd like to show you today in the next 45 minutes a little bit more on how to succeed with bioresins on injection molded applications. And to go through the agenda, we will speak about the growing opportunity in bioresins, about the overview of commercial bioresins, the bioresin challenges and best practices, the bioresin application examples, if you want, from the field, and as a last point, how Husky enables you to succeed with bioresins and your applications. So the growing opportunity of bioresins in bioresins across a number of industries and applications, bioresins have become an increasingly popular alternative to the traditional resins in the injection molding. The global market for bioresins has risen steadily over a number of years and expected to continue that growth at an impressive rate. Over the next 5 years, the market is expected to double in size. So if you look at the compound annual growth rates for the US market, we speak about 70% in between 2020 to 2030. And in Europe, for the compound annual growth rate, about 13% between 2022 and 2027. So for innovative brands and injection molders, this adds up a significant growth in the opportunity. So what is exactly driving the growth in the bioresin adaptation? So customers today, for sure, they want to understand their products, and this includes as well their packaging. Since biopolymers are derived from relative sustainable materials and can be engineered to biodegrade, many consumers feel that they are a healthier choice for the planet. Another reason is the ESG, the environmental and social governance, which drives brands and molders under increasing pressure to adopt their ESG strategies to doing business. Means that using bioresins for injection molded products and packaging helps organizations to meet their ESG targets and objectives and signals to customers that they are doing their part for the environment. And what you all know is that new legislations and regulations are taking place all over the world and putting pressure on manufacturers to reduce post-consumer waste and plastic pollution. For example, the European Union Commission implemented new laws that restrict the single-use products made with petrol-based polymers. So let's go a little bit into the overview of commercial bioresins. So what are bioresins? Bioresins are sometimes called biopolymer, bioplastic, biomaterial, whatever. They all refer to several categories of commercially viable materials that, for example, can be used for the injection molding process. And what makes a material bio-based is that they're made from whole or in part from renewable biological resource. These biologic resources can include corn, wheat, maize starch, or tapioca, potato starch, vegetable oil starches, sugarcane starch, wood pulp, cellulose. You can see there's growing more and more ideas in how to make materials more sustainable and bio-based. So let's go a little bit into what are the commercial available ones. So this overview shows you the current most common thermoplastic bioresins, which are commercially available, and each of them are providing the capability to substitute a large range of polymers and applications. PLA, which is derived from different starches, are substitute, for example, PE, polystyrene, polypropylene, and PET. Or PHAs and PHPs, which are derived from microorganisms, bacteria, fermentation, are substitute for polypropylene or polyethylene. And there's as well cellulose-based, which are extensively modified thermoplastics, which are substituting polypropylenes. So do not be cautious if you are missing any substitute material here. The list of substitutability is consistently increasing. So it's always a recommendation to reach out to resin suppliers and compounders to find the right material for your application and requirements. So because there are many other alternatives and substitutes under the development with some really promising attributes and as well optimized processing conditions. On the next, you see this one is the 2023, the production capacity overview of bioresins. And what you see on the top, the blue big piece is on all non-biodegradable but bio-based materials. I will explain you later a little bit more about this. And on the bottom right corner or the right side is showing all the biodegradable resins which are currently available for as well injection molding or other processing. And what is important is that you see that PLA still remains a big pillar in the injection molding and remains one leading biodegradable material. But like I said, there's steady growth of other biodegradable materials and alternatives, for example, PBS, PHA. But for them, the most challenging points remains the sourcing capacity and the pricing. So they need to compete against the very relative cheap PLAs. So to understand, if you're going to explore the bioresins the first time, you should understand some key terms. So when you are planning to use a bioresin, it is important that you knew a few distinctions and what it means, the terminology and features. Means that bio-based refers that the fact that the material was made by whole or partially from renewable biological resource and to use and produce the material. But it's important to understand not all bio-based resins are biodegradable. And this you remember on the chart on the previous slide was the left top big blue pie. Then we have biodegradable, which means that the item will eventually break down in the natural environment. And then we have compostable. Compostable means simply that the material is biodegradable and breaks down within 3 to 6 months, and mainly in industrial composting facilities, and releasing there some valuable nutrients and leaving no toxicity to the soil. Important here as well to understand, not all bio-based and biodegradable materials are compostable. So what are the challenges and what are the best practices in working with bioresins? On the next slides, I will show you what are the challenges. So material characteristics. Bioresins materials, they come with unique and challenging physical properties that can make difficult to incorporate them into the injection molding process. For example, many bioresins are highly viscous and require high pressures to fill the molding cavities. The behavior you can compare with a PET or polycarbonate, PC. They intend to be very prone to leakage and weepage, means materials are easily flowing in gaps between valve stems back to the cylinders. And I have some pictures later on here as well to show you what that means. They have often very significant temperature sensitivity, so undershoots causing super high pressures, while overshoots are causing material degradation and sudden degradation up to really black burnt material. I have some pictures as well on the next slides. They often build corrosive gases, and this is one of the biggest challenges as well. I have as well some nice pictures here to share. So let's go to the next point, manufacturability. Often it is intended to change material, to exchange existing products, for example, from an easy flow polypropylene to an, let's say, relative high viscous and temperature sensitive bioresin. And often a one-to-one comparison doesn't or remains unsuccessful, as for example, the part geometries cannot be filled successfully, mold ventings are not optimized, the hot runner diameters are not adapted to high viscous materials, or even the steel types are not corrosion resistant. And many other reasons which are unknown and needs to be discussed with resin suppliers. So we will have a closer look on the next slide. Performance. Using new materials brings also a number of unknowns, means especially in terms of performance. Many bioresins may not perform as well as traditional materials in terms of product preservation, longevity, safety, and as well other key performance criteria. All these unknowns need to be addressed in order to achieve a successful adaptation to your product and requirements and into the bioresin itself. And the quality. So quality is another area where bioresins may not initially meet the same standards as traditional materials. So molten bioresins tend to be very corrosive, which can compromise equipment, lead time, quality issues, performance variations, and even components failure. So this may require the more frequent equipment inspection and maintenance to ensure a consistent and predictable uptime of your hardware. Let's go to some pictures and examples. Like I promised, on the left side, what you see, we call this a manifold plug, and hope I can show you. This is another version, just simply the same. What you can see, the angled surface in the picture on the left is showing the angle here, which is in direct contact with the melt stream. And it's not, what you can see, it's not really the material itself corroding the materials. It's the gases which are flowing in between on the side. You can see that heavy corrosion. It is really not the melt stream which is causing the corrosion. These are really the gases. And the same you see on the second picture, which you can see here. That's the nozzle tip, and what you see, the corrosion is happening really on that side. I hope I can show you that very well. So it's really corroding in an area which is not even in direct contact with the plastic. So the plastic is usually here on the front. This is where your part is sitting. So the corrosion happens inside the system and really is an obvious, let's say, effect you can directly see. And on the very right, this is from a coffee capsule, similar to this one. The core, and you can see that on the core you have some corrosion, and that is a fact when you are changing from a easy flow polypropylene to a high viscous bioresin. It can cause corrosion because your mold is simply not adapted to stainless steel components, protecting against the corrosion behavior of that materials. On the next slide, this shows you a little bit the weepage and leakage challenges. On the left picture, what you can see, that is a sprue. There is your machine nozzle, so the top right corner is a heater. You see a little bit of it, and underneath that are the two bolts, which one of the 4 bolts, let's say, which are connecting the sprue to your manifold. And you can see there's some black material coming out, and this black material is coming out of an area which usually has tight tolerances, and is really screwed to not give any leakage problems here. But the material becomes so high liquidity when you are burning it, like you see here, that a manual cleaning often is necessary to do here to get the system free of all contamination and black burnt material. And then on the right pictures, it's basically both showing the same area. That's the actuation cylinder, the piston of a valve stem needle. And on the middle picture, you can see it, the white material in between the piston and the bagger pad of the manifold is full filled of material, which is flowing back between the thin gaps of a valve stem guidance till back the actuation cylinder. And you can imagine there's no movement anymore. This valve stem is fully blocked. You cannot actuate anymore, means you need to open the system, clean the system, and to get rid of the material out of your cylinder to further process and produce your parts. On the right side, it's basically the same, just in with the black material, burnt material. So on the left side, I would say it's more kind of standard material flowing back. On the other side, it looks more it was degrading heavily and then flowing back, like on the very left picture. So what are the best practices for succeeding with bioresins? So first of all, optimize the application design. Optimize the hot runner and controller. Optimize the manifold design and ensure a consistent preparation of the bioresin. So there are basically 2 points which are related to the hot runner supplier, which is, let's say, on the Husky side. And there's point number 1 and point number 4, which is more dedicated. Point number 1 on the molder side or on the partner, the product owner, and then the point number 4 is a molder side. And I will go a little bit more in detail what this means. So it is important to conduct an in-depth review of an application and bioresin itself prior you start any manufacturing steps. This is very important. Ensure that the hot runners and controllers are optimized, the manifold design is optimized, and consistent preparation of the resin. So let's take a closer look on the next slides. We have global teams, application engineering teams, and I'm leading the European one, but we have as well in the other countries the same teams, the same capabilities. So conduct us for an in-depth application review. We are supporting with our tools, MoldFlow, FEAs, and test lab capabilities to guide you from the beginning of a bioresin project till the end. So that means understand the cavity fill analysis. And this is one of the most challenging points for materials, is that we don't have rheological data. Rheological data is expensive to create, and not each compounder, you can imagine, can afford to create rheological data for mold flow filling analysis, for example. So the cavity filling analysis is very difficult if you don't have the real rheological properties, but you should always go into contact with the suppliers to understand if they have maybe this data or not. If they have this data, it's perfect. If not, then we need to look for alternatives, how to find the best possible way in optimizing your system that it will be right the first time. And this can be, for example, consulting a resin test. A resin test, our experts would evaluate in that test if the material, how it behaves, how it is in terms of pressures, residence time, and how it is comparable to other materials we already tested. And based on this, we can get a feeling and guide in which resins we could use for substituting them into fill analysis to get the best possible results. Then we can review thermal FEAs, which are also important to have no undershoot or overshoots within the hot runner systems. Means each of the system will be individually reviewed, that we are within the specific supplier recommendation processing windows. Then we have to evaluate, do we need to apply high pressure guidelines, means drilling the channels in specific angles? Do we withstand the pressures, and how we can scale up the system from low cavity maybe to high cavity systems. And one of the most important points is the low delta T temperature gate detail design. That means you should review that you have an efficient cooling, how your material is behaving with this new material. Is it sticking on the valve stem because it's too hot? So we can as well support here in doing FEA studies on your cooling to review and optimize the system in the way that you get a high quality product with a good output. So to ensure the hot runner and controller are optimized for bioresins, and this should include, we should apply corrosion resistant components whenever it's needed. We should have V-pitch mitigation components, means tight gaps, maybe with coatings and other guiding tolerances which are protected. We should have a plunger valve gate to ensure always a good gate quality, to ensure that no materials are flowing between tapered areas and that you have a good gate quality cut. You should have an individual tipping control, which is, let's say, usually not a question, but sometimes there's the idea to save some zones and to make a group control on the tips. This, for sure, you should avoid. And what is also important, you should have an improved heat distribution all along your melt channel path to avoid any overshoot, but as well undershoots. And the last important point, and this, if you remember back the picture on the previous slides with the black burnt material, an I/O connection to the injection molding machine is always recommended to avoid any degradation, because biomaterials tend to really degrade suddenly and fast. That means when you have a cycle breakdown and someone forgets to shut down the heaters to a certain temperature, the machine should automatically react and shut down the hot runner to a level which the material cannot create any damage to your system. What are we doing in kind of optimizing manifold design? So we ensure that all our systems are geometrically balanced and as well rheologically balanced, all from the melt channel inlet till the outlet to the cavity. We avoid enriching manifold heaters, so to have the optimum thermal profile, to have the control between the back of a manifold and the front, for example, which is often happening that you are bridging them together to save number of zones. Your channels should be optimized as well for low pressures, reduced shear rates, and reduced residence time. And what you can see here is that low pressures and reduced shear rates requires big channels, while the opposite is minimum residence time requires small channels. And all our systems are running through a fill analysis prior we start manufacturing steps to optimize all this in in an optimum way, but I will show you later on a bit more about this. Thermal uniformity of a manifold design is also important. So Husky performs for almost each individual project a thermal FEA. What means almost? Almost means that, for example, if you order a repeat system which already was performed with a thermal FEA, we would not start another FEA. So this means simply almost, but we do for each project, we do in thermal FEA prior to any manufacturing steps. And this means that we are adjusting the heater wrapping, the number of zones, the thermocouple placement, and melt channel layout with the heat sinks and all the manifold profile. The hot runner designer optimizes it in a way that the thermal uniformity of the system is acceptable prior we start any manufacturing steps. And once there's something out of the rules, it will automatically end up at our desk, and we would directly go into a discussion or solutioning to find a way to get it better and optimized. So this procedure ensures that the system is individually adjusted, optimized, and for your application resin requirements, and ensures that you have a consistent melt stream all along from the inlet till the outlet, as well on the hot runner blades on the outside, that you don't have any hot spots there. For the melt channel optimization, and this is what I said previously, is that we need your help. We need the help of the project leaders to understand what is the resin, the family, potentially the additives, and the similar grades which are maybe available for flow simulation. So we can consult resin suppliers, we would consult maybe the compounders or you directly to understand a bit more about the materials. But we as well need to know more a little bit about the expected parameters you want to run it. So injection time is for sure leading shear rates, pressure drop, etc. So that means as well we need to get an idea of the injection time, which we can get from the field analysis, but maybe you have already similar applications in the field running. We need to know the recommended melt and mold temperatures. We need to for sure to know the drop locations where the hot runner distances of the drops. We need to know the part geometry with volume and the thickness distribution. And what is one of the most important points to understand, what are your performance requirements? Do you have a cycle time target? Do you have a color change target or even a balancing target on your parts? For sure, these are all the parameters. As much inputs you can give us, as better it is. And as an output, we have engineering software, which is based on MoldFlow software, is calculating the system for optimized geometry of the hot runner system with optimized melt channel layouts, with optimized melt channel diameters to achieve the best possible performance on pressure drop, shear rates in the system, shear rate at the gate, temperatures increased inside the system, and residence time. And then we are at, point number 4, ensure a consistent preparation of your bioresin. So here the best practices are that you ensure the adequate drying before the usage of the material. So follow the supplier recommendations and as well avoid exposing to atmospheric pressures and conditions, atmospheric conditions after drying, to ensure that they are not taking moisture anymore from your dryer till the machine. So keep the distances very short. Keep the package sealed until they are ready to use. And reseal any unused materials, store them in a dry place, ideally inside the same temperature conditions like you store, like you produce your products as well. So it's very important to follow resin supplier recommendations for drying, melt temperatures, mold temperatures as well, the screw speed and the back pressures, as well as the total residence time. And here we see the most challenging points is that often suppliers and molders tend to increase the temperatures to fill the cavities easier because they are taking very high pressure drops. And then the material suddenly burns. So you are always in between of capabilities, and you should ensure to really stay within the supplier recommended values here. So these are the capabilities we have. We have teams everywhere in the world. Contact us, consult us. We help you from the beginning of a project till the end to guide you through the right steps, and we are helping you with all the engineering tools we have available. Let's give you a little bit of example on what we do or did in the past years. Only a few ones. For example, this one is cutlery, which was made from a PLA. And here we have between 4.6 to 6 gram at a wall thickness of 1.2. And you can see that 32, 48 drop, so high cavity systems are possible with these kind of materials if you take the right actions at the right time. Then coffee capsules. So here as well, we have from, let's say, big capsules to really small capsules. We have everything in the field. Means we have 2.9 to 5 grams. That is just, for example, the samples I have here, with a wall thickness of 0.6, with partial even going down to 0.15 millimeters of thickness, where the breakage area is. And here we start with prototyping on small systems, even scaling up to high cavity systems, 48 top as well. Caps is as well a target market, so PLAs are as well used here, 2.2 grams, 0.8 millimeter wall thicknesses, so a standard PP closure cap you would use. And here as well, it's currently, here it's written a 4 drop, but we can have as well high cavity systems as well for these products. So how can we enable you to succeed? And this is, like I said, we have the application engineers with all their tools, and we have a big lab here in Europe as well, and access to a lot of different tools. And I will show you on the next slide a little bit more about what tools we have available. And even beyond that, you can always contact us. We will find a solution and how we can simulate the best possible or closest possible cavity design and guide you to the right testing. And you are welcome as well to always come here to see live run and to learn with us together your new materials and your new products. So for example, this one, we call it the Petri dish, but it's just called like this because it's a 70 millimeter diameter, and the thickness here is a variable from 0.5 to 3.5 millimeter. You can see it's a simple design, but gives us a big impression about the material properties, running low speed, high speed, low temperature, high temperatures. We make residence time trials and all these kind of things. We can test the extremes in our lab with this tool. And it's a 2-drop, 2-cavity system. We can test here our smallest until almost the biggest U750 nozzle. It is available as hot tip, open nozzle, and as well valve-gated system. On the next slide, this is more addressing the packaging, thin wall packaging market for food containers, or in that example, it's a cup, a drink cup. Here as well, we have 2 different cores with 7.8 and 11.5 cubic volume. So we can try very thin walls from 0.4 to 0.7, and the other cavity design has 0.6 to 0.9. It is a single cavity system only, means a single nozzle only, but gives us a really good insight of a material on what we can expect of filling cavities with very thin wall thickness conditions. Then we have the coffee capsule, which is as well comes with variable wall thicknesses between 0.3 to 0.6 millimeter. Gives you at the end 2.1 to 5.1 cubic centimeters of volume of the part, and is available as a 4-drop system. Ultrasync E driven means available as well with different nozzle series, your Ultra 350, 500, and 750. So we have a large range here we can test to as well simulate your product and to understand the materials. And like I said, we have all over the world a lot of other tools available. That is, for example, the key cup on the top. Then we have sauces, we have food container packaging, we have we call it Tassimo, Dolce Gusto, and Espresso designs, and they are available as mono and multi-layer testing tools. So that means we can even make trials with you together. If you are interested for the multi-layer testing, contact us, and we will guide you to the right, solution. So that being said, Husky offers right combination of experience, expertise, and technology to ensure a successful adaptation of bioresins to your application. It takes all three of that, to get right the first time. So one more important point is to mention, Husky does not provide resin recommendations. For instance, recommending moving towards a specific bioresin over an alternative. This remains on the resin suppliers, or more on the product designer and experts to guide here in which materials are the right for the product. And there carefully review the product requirements, the compatibility with your needs, and from that point on, Husky can support you with experience, expertise, and technology to succeed. Speaking shortly about the technology, so Husky offers therefore a system solution ideal for successful adaptation of bioresins in new injection molding operation. Our ultramelt hot runner is a key component of that because it's engineered for application requiring excellent process thermal control and the minimal effects on the resin chemistry. The ultramelt features 100% non-reactive surfaces and stainless steel components to preserve the sensitive chemistry of bioresin materials, minimizing corrosion or other previously mentioned challenges. So that means with the ultramelt, the full melt channel pass from the inlet of the hot runner, from the sprue, over the manifold bushing, the valve stem, the nozzle housing, and nozzle tip is fully protected and optimized for biomaterials. And basically now we are at the end of my presentation. I hope you have enjoyed it and you could take some useful learnings and information with you for taking your next step in exploring the bioresins world. And Husky would be glad to follow you on that path. So don't hesitate to reach us out anytime. Our teams are there. And I like to say thank you for your interest, your participation in this webinar. And I'm glad now to answer your questions.
Yes, thank you very much, Oliver. And thank you, everybody, for your attention so far. Like Oliver mentioned, we're now heading to the Q&A section of this webinar. We already had some great questions coming through, but obviously, please continue to send them in. And if we don't manage to get through all your questions, I'm sure the team will follow up with you individually afterwards. The most popular question we had today actually is, can you provide some specific examples of a good use of bioresin?
So examples, like I said before, it's single-use plastics and single-use plastics. So you can imagine that it can be cups, it can be containers, it could be cutlery, it could be coffee capsules, all kind of products which I just mentioned earlier are capable. And I know as well that there's an outlook on bioresins like PBS, BHA, which are promising as well to be adapted in the medical world with getting approvals and certifications here as well. So yes, there's, let's say, upcoming a lot of development from the compounders and as well from the resin suppliers in that direction in any market. So let's say give it a try, contact your resin supplier you are interested in or it's a product you like to change. And I'm sure you will find a good compromise and a solution for your application.
Thank you. And somebody else is asking which tests could be run to prevent corrosiveness and or optimize performance when using new bioresins?
What tests? Can you repeat that, please?
Which tests could be run to prevent corrosiveness or optimize performances when using new bioresins?
When using new bioresins, so first of all, it's important to understand if the material is creating corrosive gases. So not all resins may have a corrosive interactions to the system, but we know from PLAs, for example, PHAs, they usually tend to very corrosive and to create corrosive gases. And to test, you should first of all run it at lowest temperatures possible. The challenge here is that your pressure will increase and maybe your machine will run at the limits. So that's why often molders are tending to run higher temperatures, and this again causing corrosive gases. So I think it's very difficult to test it in short term. You need to do it in long term, and this is why we have extensively tested in our labs different kind of materials. And let's say the ultra melt is one of the products which came out of that, is protecting the complete hardware against corrosion. I hope I could answer this as the best possible answer. The thing is that from the mold side, it's for sure a different challenge, which maybe a mold maker can help better.
Thank you, Oliver. And somebody else was asking for a bit of clarification. And they ask, what do you mean by ensure consistent preparation of bioresins?
The consistent preparation means that you should ensure that with the back pressure and with your rotation speed of the screw, and as well the temperature setup, you always prepare a consistent melt and homogeneous melt. That is very important, and that always your materials are dried in the same conditions. So around 250 ppm. That is what I know usually is used for drying biomaterials. But here it means that you keep always a consistent melt preparation, that your machine is repeatable and always delivers a good melt with the same quality, let's say.
Thank you. And somebody else is asking, what is the maximum barrier level for these materials?
This I cannot answer. I think that is something more what the resin supplier has to answer. This is not what a hot runner supplier can answer this question. I'm sorry for that.
No problem at all. Somebody else is asking, is the corrosion more linked to the viscosity of bioresins or to each formulation?
No, it's a principle. We are talking about polylactic acids, for example. So the word here already says it. It's the nature of the bioresins, which is causing during the processing gases, which together with the humidity and the environment is causing the corrosion interaction. So it's not linked to the viscosity. It's purely about the material inherent properties. And again, the chemistry maybe is better to answer here as well from the specific supplier of the material.
Thank you. And we have a couple of questions about what experience you have with different materials. So somebody's asking, do you have any experience with PHA? And then somebody else is asking, which other materials do you have experience with apart
Sure.
from PLA?
So apart from PLA, we have tested, maybe you have seen that on the previous slides. I'm not presenting anymore, right? So on the previous slides, I was showing some of the examples. So we tested PLAs, we tested highly modified PBATs, PHAs, PHBAs. We had different kind of blends. So we have really tested, I would say, hundreds of different grades in the meantime, and as well good connections with a couple of resin suppliers in the meantime, where we do consistently new trials, new formulas, and so on. So we are learning as well with the market together, and we are trying to step in more and more. So we have a, if you're interested in something to test, come to us. We can try it. We can evaluate if your material specification, first of all, is able to injection mold. That is one of the important points as well, because often materials are optimized for extrusion, and we need first to evaluate, can this even be injector molded? And this we can do. We are open to test each time.
Thank you. And somebody else is asking, what bioresins do you feel are not effective for injection molding?
What? I'm just, I see the pressure. What do you mean by? Yeah, that's what I said. It depends on the formula. So for sure you can, what is important is that you don't add plasticizers, right? You want to keep maybe the biodegradable properties of the materials, and you should not add some plasticizers. This I know. So it depends really on the material characteristics. And like I said before, extrusion grades can be challenging because they are optimized for different kind of process, but as well blow molding or film extrusion. So all these kind of grades can be challenging, but like I said, this we would evaluate. We have as well extrusion grades which are running fine, and we can find out the right way for you.
Thank you. And somebody else is asking, have you seen an increase in bioresin usage, and how does it impact hot
Absolutely.
runner maintenance intervals?
Absolutely, that is a good question. I started in 2005 at Husky, and the first trials I have seen with PLA was in 2005, 2006, and there was the first suppliers which had a little bit of an outlook. They wanted to get touching with new materials, and let's say it was very quiet afterwards, and then in the last 3-4 years, it's steadily increasing the inquiry. So we have, let's say, each month a couple of requests, which in the past was only once, twice per year. So there's a huge interest in the meantime, which is mainly driven by the European laws implemented. And what does it mean for the maintenance? I think I've said it a little bit earlier in the presentation. Preventive maintenance intervals are mandatory. I mean, that you should do for all kind of resins you are processing. Biomaterials, I would say, tend to be more often preventive, at least at the beginning. If you have a new material, you should learn yourself from it. You should learn how it behaves. And if you see that it is better than expected, you can extend your preventive maintenance intervals to longer distances, let's say. But at the beginning, I would ensure to have a bit more often the preventive maintenance intervals, yes.
And another question we had, what experience do you have with high temperature or corrosive resins? What is the difference compared to bioresin?
Yeah, basically, you would not imagine, but basically they are very similar. So it's a bioresin has very low temperatures. That is for sure one of the big major change. But from the corrosiveness behavior and from the let's say applications and the application hardware you use from the hot runner point of view, they are very similar. We have a lot of experience with high temperature corrosive materials from the past. in electric components. For sure, peak, pi, PSU, PPSU. And from that learnings, we also transfer to the corrosive materials like bioresins. It's just the temperature which makes them different. And what makes also different is that often the high temperature engineering materials additionally have fillers, and fillers in additionally have some abrasive behavior, which is not the case for biopolymers. So that is only from the hardware point of view a little bit of different, but they are very similar. That's true.
Thank you. And somebody else is asking, can a traditional hot runner system be upgraded or revised to accommodate a switch to bioresin? In brackets, if the original system was for a different resin.
Also, a good question. This is quite common. This question, at least in the last, let's say, 2 years, growing. This requests molders tend to going more and more into the bioresin usage, and they're requesting us that existing systems can be upgraded. In principle, I would say yes, they could be upgraded, but you need to differentiate if it makes sense, because maybe you need to exchange the complete system, especially when the material is be corrosive, so that it maybe makes from the investment point of view no sense. But in principle, it's possible to upgrade systems. If it makes sense, our teams would individually decide and review with you together what is the best path to go. For short-term testing, if you are interested to first of all see the compatibility with your product, you can reach us out. We can evaluate if the channel sizing would fit to your resin, and then you could make some short-term trials. For example, this is possible. It should not corrode from one to the other day. So this one is more long-term. So for short-term testing, you probably the hardware can be used to make the next step to decide we will invest in a new system, for example.
Thank you. Okay, I think we have time for a couple more questions before we wrap things up. Somebody's asking, normally, what is the time scale for Autodesk to incorporate rheological data for a bioresin grade onto the mold flow database? Quite a specific question there.
That is a specific question, that's true. So I'm not directly in contact with Autodesk if they are characterizing themselves, but we are using external laboratories sometimes to characterize materials. For sure, it has a cost impact. The cost impact needs to be covered, but usually it takes not too long time. My experience is around 2 to 3 weeks, but that depends really on the specific laboratory you contact and consult to get this data available for mold flow. So usually you should be able to get this material characterized very soon. It depends on which company you're consulting.
Thank you. And yeah, time for one more question, I think. What are Husky's capabilities for testing new bioresins?
So the characteristics MFI, TM, to run new bioresins, basically we don't need so much. We just need to know the safety of the material, if there's some specific considerations to do. And as well, what we need is melt temperature, mold temperature required. What is the expected residence time, so that we do not, let's say, destroy our hardware because the material is immediately burning. But we don't need so many in-depth details of a material. We often, like I said before, we often have resin suppliers that are sending us new materials, new compounds, and we are trying them the first time. There's no data sheet existing. So basically, I don't think we need so much information. The minimum is residence time and as well the expected processing temperatures you have.
Great, thank you very much, Oliver. So yeah, that brings us to the end of today's webinar, and thank you everybody for joining us. This webinar will be available on demand within the next couple of days, and you'll be sent a link to access it in case you want to recap on anything you've seen in today's session. So that just leaves me to thank you, Oliver, for being our speaker today, and thank you everybody for watching today. Thank you very much. Goodbye.